Across the nation, roads are crumbling, and the bridges that span or link these roads are going with them. In fact, over 40% of the nation's 575,000 bridges today are in need of repair or replacement, and a majority of those are in rural communities, where small bridges cross over rivers, streams, and wetlands. Rhode Island is no different from the rest of the nation when it comes to road conditions. Many of our 700 or so bridges are in rural areas, ineligible for federal highway assistance when they need reconstruction. The State Department of Transportation is responsible for monitoring their condition, posting load restrictions, or closing those that are unsafe altogether.
In terms of percentage of bridges, I might pull a figure of like 25 to 33% of the bridges are needing some sort of work. Of that, a good percentage will need replacement.
You know what we're going to have to do? When you lift those planks, we're going to have to store them off to the side, bring the load bed out, load them on the load bed, and cart them out, because there's no way you can put these in the truck.
Walter May, the Public Works Director for Foster, Rhode Island, has become well acquainted with the problems of bridge deterioration in a small town.
A deteriorated road is one thing, but a deteriorated bridge can shut down a whole section of town. And the rating of this bridge was down to about 6 tons, which would prohibit school buses, fire trucks, some emergency services, contracted for services, deliveries, all of those types of traffic that have to have access to the public have to detour around so they can avoid a low-rated bridge.
Recognizing this threat to America's crumbling infrastructure, the United States Congress funded the Timber Bridge Initiative in 1989. Using methods pioneered in Ontario in the 1970s, over 200 demonstration timber bridges have been built across the country to show that small communities can replace their bridges in less time and with less money using locally grown, pressure-treated wood, rather than concrete and steel in construction.
Rhode Island RC&D is very interested in this because it does promote rural development. It has local people solving local problems and using local resources to do it.
In this video, you'll see how, through a collaborative effort of federal, state, and local agencies and businesses, a demonstration timber bridge was constructed in Foster on North Road, spanning 22 feet across a small river. You'll see how this bridge was engineered to use local underutilized timber that can result in cost saving in materials, achieve the same traffic load bearing capability as steel and concrete, be constructed with minimal equipment and by public works crews, be installed in a fraction of the time required for steel or concrete bridges, and reduce maintenance costs over time.
In typical bridge construction, for a lot of the steel and concrete bridges, you have steel girders and then you have a deck. In this case, for the Foster Timber Bridge, you have 2x10 red oak planks, which are all bolted together with about, I think, 60,000 foot-pounds of torque. And it has plates pushing it together, too, with the nuts. And that makes it like one, basically, 10-inch thick plank. And it's incredibly strong. It serves as both the deck and the girders.
These bridges are not quite the old-style timber covered bridges that everybody imagines. You could put that type of structure over one of these. They look pretty modern. They are contemporary looking in their design now. You will still be able to tell it's wood. It'll be covered with asphalt, so you won't, when you're driving over it, you won't know it's wood.
All of the bridges in Rhode Island traditionally have been designed, that is, interstate bridges and every other one that we've had a part to do with, have been designed for what we call a 20-ton two-axle vehicle and three-axle tractor trailer that weighs 36 tons. And this particular bridge is designed to meet those loadings, and I think it may exceed those loadings. It'll be able to handle any of the normal traffic that a bridge would be required to take.
A 20-ton capacity will be more than enough for school buses, emergency vehicles, and trucks passing through North Road. But the old bridge was only 14 feet wide, and the approach had a skew in it.
Talking about a road realignment, widening the bridge, increasing the capacity, and changing the construction of it to accommodate an easier replacement when the life cycle of this bridge expires.
Because the bridge needed more than a deck replacement, An engineering firm was brought in to survey the site and furnish detailed plans of the bridge specifications.
We were able to furnish the town with not a very comprehensive detailed plans. We tried to minimize the cost involved, but we gave them adequate plans so that they could build a bridge, from some set of engineering plans which are required almost on all projects. Regardless of how simple the project may seem, to some degree you do need some expertise involved in planning the project and putting that down on paper. On this particular bridge we're using 2x10s. That was all that was required for this span length, which was 22 feet.
We are using red oak, which is native in Rhode Island, so the locals could inexpensively get the wood for the bridge. And in other states, they have used Douglas fir or southern pine or different types of wood. So we have to actually do some tests to see the applicability of this type of wood for stress laminated bridges.
The timber that we use right now is red oak. That's probably one of the most predominant species in the state. Some communities right now are working on acquiring open space and making town forests. The savings there is that they don't have to go out and buy the timber, they already have the timber. They can just go to these areas, harvest the timber, and then utilize their own trees for their own bridges. In Rhode Island right now, trees are growing 3 times faster than we're taking them out. There's so many trees growing. Proper utilization helps us manage our woodlots. We're at the Red Oak Tree Farm here in North Scituate. It's a tree farm managed by Steve Thomas. Does an excellent job managing his woodlots. Like many other tree farmers here in Rhode Island, these lots are what we come to find the wood. This is a northern red oak. It's about 36 inches in diameter. Most of the trees that were cut for this timber bridge are right from the local area, Foster, Gloucester, Scituate. We didn't go out and mark this timber specifically for this product. We went to the mill and graded it at the mill. Then we selected the better quality stock here, right in the Foster shed over there to be treated at the lumberyard.
What we do is we take the planks, these have all been sawed and squared. All right, then we lay them on the rollers and we put a template on there, mock the template, okay, and then we slide them on the drill press and we drill the holes. Then after all this process is done, we send these out to be pressure treated at Permatreat out in Connecticut.
The treatment of the timber is done right over the line in Connecticut. That treatment is not as dangerous as it used to be. What we do is we have a clean treatment done. It means the creosote doesn't sweat, doesn't come out of the wood as easy. It's pressurized into the wood. And when you're handling it, you do have to wear gloves. It can burn you. But as for it dripping into the river once the bridge is built, that won't happen because it is a clean treatment. Well, the creosote pretty much keeps the water from getting into the pores of the wood and causing the fungus decay and letting insects get into the wood.
What is supposedly unique about this particular type of structure is that, number one, it's pressure treated. Number two, it's pressure treated after the holes are drilled. And then number three, it is laterally post-tension to keep it all in compression, keep it all very tight and sealed off from moisture, etc.
The I-beam, you can see there's some deterioration here.
Road salts and de-icing compounds are the enemies of concrete and steel bridges, and regular painting of the steel beams is necessary to prevent rusting. But pressure-treated timber bridges are unaffected by salts and resistant to moisture. Less maintenance means a long-term cost savings to the towns.
It should be a very low-maintenance bridge, and it's not affected by the elements. It's not affected by road salt.
This bridge will have a covering of asphalt, which will protect it. If that asphalt starts to break up and crack, it should be probably periodically replaced. And this will kind of protect moisture from intruding into the wood below it.
Concrete and steel bridges show deterioration, significant deterioration, in a period of, say, 20 to 25 years, at which time we have to get in and do something about patching and painting and fixing. The Timber Bridge Initiative folk have indicated that these bridges will last 75 years.
Another advantage to timber bridges is that they take less time to construct than steel and concrete. Once a wetlands permit is obtained, the abutments are ready, and the engineering plans are drawn up. The rest is just putting the pieces together. Ease of assembly means less downtime for the bridge, and a savings in labor and equipment. The U.S. Forest Service reports initial studies indicate timber bridges cost approximately 20% less than steel and concrete equivalents.
A timber bridge has certain advantages in that I think they can be built easily by a municipality that has a certain amount of skilled or even semi-skilled help to help put it together. It doesn't require a great deal of equipment, and most people know how to work with wood.
So I understand that it's possible to go ahead and install these bridges, to have the old bridge deck taken out and a new one put in within a week's time. We're talking weeks for steel and concrete, for the concrete to cure, and a lot of downtime where the bridge is closed in steel and concrete, where you can have it done within a week or 2 weeks with timber bridges. Just because you're manufacturing the deck right there, you pull the old deck out, you make some cleaning up and some alterations, then you drop a new one in and put your wear surface over it.
So it causes a lot less inconvenience to the motoring public, provides for greater safety in a much shorter period of time and less rerouting and detouring of traffic. There is a system of long rods, which are called post-tensioning rods, that go through these pre-drilled holes, and they're secured on both ends by a system of plates and nuts that compress the lumber. But I would expect that we should be able to assemble it within several days after we get the material on site, and I expect it not to take more than 1 day to hoist the bridge deck onto the new abutments and secure them. There'll be load cells embedded in the deck of the bridge, and URI are going to come out here and do readouts periodically, and they'll be able to tell what the inside of the bridge is, how it's taking the stress.
So what we will be doing actually is we'll use these load cells. We'll thread the load cell in the rods, and we'll be placing one more steel plate exactly like this one on the other side, and we'll be tightening the load cell with the force about 26 to 27 kips. And we'll be monitoring this force using a load cell readout box. We'll be taking a reading before we install the load cell, and then afterwards once a month, and by the difference between the two readings we can figure out how much is the force and how much does it change. If there is a need in the future, we can come back and restress those rods to their original force.
And cooperative extension at URI helped to get engineering involved, and by doing this post-testing we'll be able to see how the bridge is changing, what needs to be done to keep it up, and it will provide a really good record for other bridges as to how to handle the bridge after it is constructed. From the community revitalization point of view, it's mainly getting the community to think that it has a resource that it can do something on its own.
We've proven here with some measure of success that public works people do have the skills necessary to build one of these. They'd rather be doing this than some of the other tasks that they have to do. After they retire from this job, they'll be able to run their grandkids over it. And I built that bridge back in the 1990s. The Timber Bridge initiative here I see as a boon to any municipality that has the resources and the talent to get involved with these. It's a renewable resource, wood. You can, with average skills, mechanical skills, local people can do it. It would promote local economy, and it allows the municipality to replace part of their infrastructure that's been deteriorating for years.